Cool. And we still have full batteries, so that's good.
Yeah.
Oh, thank you. All right, guys. So, today we're going to do something which is kind of like a little bit now for something completely different style of lecture compared to the last couple things that we've done in this class. Right? We spent a lot of time doing differential geometry and even our approach to shortest path, which is in some sense a global calculation, still used a lot of differential machinery. Today, we're going to talk about the opposite problem, which is I give you distances as input, and you want to find the piece of geometry. And somehow the machinery that we're going to need for these kinds of problems is quite different from what we've seen so far. Incidentally, the image at the top of the slide is mostly because your instructor is a weirdo. Does anybody know what this object is called and why it has anything to do with these problems we'll talk about today? Yeah, this is called a Swiss roll. Yeah. I don't know about the Swiss part, but the roll part makes a lot of sense, yeah? And essentially there's a data set we'll see later in lecture which is extremely famous in sort of old school machine learning papers on these style topics where the Swiss roll, if you think of just that piece of chocolate cake here, you could think of as an intrinsically two-dimensional object rolled up in a three-dimensional world. It's a frustration many of us have. And essentially, our goal in today's lecture is to unroll the Swiss roll, right? To identify the 2D structure that's hiding in the data that we have. Cool. So a different way of understanding it is that in our last couple lectures, right, we've talked a lot about going from an embedding to distances, usually on our favorite 3D bunny model here. And now our job is just to flip that thing backward. And initially this might sound like kind of a made up problem. Like when would you have access to distances and not access to the shape? But it turns out it's pretty realistic in a number of different scenarios. And in fact, this is a problem that comes in many different communities under many different names. So in statistics, you probably heard of this as maybe dimensionality reduction. So in that case, you do have an embedding of your data, but it's in a space that's not particularly reflective of the structure that you really are looking at. Embedding, obviously. Parameterization is another big one, right? Like, so for example, in computer graphics, we talk about parameterizing surfaces, which is like taking a 3D thing and mapping it into the plane. And of course, there's things like manifold learning, where the idea is that you're trying to identify and leverage this sort of structure inside of your statistical or learning procedure. Is sort of built into the way you do your data analysis. But all of these are roughly the same kind of problem, and you'll see in today's lecture, we'll grab papers from a lot of different areas that are basically using the same style of machinery, which is kind of fun. So the basic task that we'll consider today is given some expression of pairwise distances between points, and we'll see that that comes in a lot of different disguises. Can we extract an embedding? Where an embedding is really an explicit list of points in some space, where the distances between those points in that space at least approximate the distances that you were given as input. By the way, there's a colleague of mine at Harvard, Steve Gortler, or Shlomo Gortler, who studies a really interesting variation of this problem, which we won't cover, if you want to read some really scary math, where they say, what if so the input we're going to consider today is, I give you a matrix of pairwise distances between xi and xj, but I don't know where the x's are. He considers the case of, I give you a list of distances, but I forgot how I arranged them in a matrix. I just gave you a long list of distances and told you that they're distances between pairs of points, but I forgot the label of what pair. And the question is, can you reconstruct from just that list? And the answer actually is yes, often. It turns out that somehow the ordering of that list is a remarkably small piece of information relative to just the values that are there, which is a weird thing that I haven't totally bonded with geometrically. Yes? That's a great question. Yeah, so the question, in case y'all didn't hear, was when I say distance, do I mean distance like in the extrinsic space, distance along the embedding, for example, on that bunny, would they be distances in 3D or distances along the surface? The answer is both, we'll consider today, and I'll try to make it clear which one is which when. If you're ever unclear, feel free to stop. Yep. And that's related to the second question I've put here, which is, for example, what dimensionality would you need to compute one of these embeddings? And even if it's always possible, yeah? Which isn't a priori totally clear when you can do something like this, yeah? So so far in this class, we've put really, really strong assumptions on the geometric objects that we've considered, right? For the most part, we've thought of them as submanifolds of Rn. In several lectures, we've specifically thought of them as two-dimensional objects. It turns out if you squint at the last couple lectures on geodesic distance, you'll see that that's not really necessary or critical. But it certainly was true for curvature, and in fact, curvature of high-dimensional things is a topic that's a little bit scary if you're not used to thinking about it. But that aside, today we're going to put extremely weak structure on a lot of our data. And this is a kind of a cool theme in the applied geometry world, which is that geometry really is everywhere, right? It's not just 3D surfaces and computer graphics. It's also, road maps, or even more vaguely, like, survey data where you ask people whether you think things are similar or not, right? That's some notion of proximity. And there are a lot of different tasks that involve just using that weak structure to still do some interesting inference. So probably the weakest structure, well, arguably they're weaker, but one weak structure you can put on a geometric space is just to assume that it's a metric space. Yeah? And so this is some set, M. I probably should rename it something else since we've been using M for manifold, but too late for now. And M is equipped with a function D that takes in 2 points in M and outputs a number, and D stands for distance. Yeah, and there are a couple axioms that we're going to use to distinguish a distance function. I think you guys can all kind of believe these, right? The first one is saying that distances are, by the way, there's a for all x comma y hiding here that I haven't written down. So the first axiom is saying what? Distances can't be negative. We buy that. Second one is saying if the distance between x and y is 0, then x has to be equal to y, and vice versa. We'll see that the second property isn't always terribly critical for a lot of the algorithms that we consider. The third one is that distances are symmetric. It takes me just as long to walk to Magnus as, well, I was going to say for him to walk to me, but he's much taller than I am, maybe for me to walk back. But in any event, and then the third object, which is actually really the one that distinguishes distance functions from other things, is the triangle inequality, right? Which says that it's always cheaper to go directly from x to z than to go from x to y and then from y to z. Yep. Okay, notice that implicitly, if we combine that with property 2 here, right, this is a strict inequality except when x equals y. Yeah? Okay, everybody with me so far? So this is sort of a weak notion of what it means to be a geometric object in some sense. But notice that this is a much weaker structure than, for example, when we talk about manifolds, right? It's not clear what it would mean for this object to have curvature. In fact, it's not clear that all metric spaces have curvature. It's actually an interesting theory question you can go back and ask. And indeed, a lot of the kind of derivatives that we've been taking the last couple lectures really don't necessarily imply. For example, a perfectly valid metric space consists of 2 points, which are just isolated from one another, and the distance d is 0 if you give it the same point twice, and 1 if you give it 2 different ones. Yeah? Perfectly valid metric space. Does it come with an embedding? No. Can you find an embedding? In this case, yes, but hopefully you guys can see the distinction. Cool. Okay, and of course there are many examples of metric spaces. The one that we all know and love, of course, is Rn, and we can equip that with many different norms, depending on, instead of the square root of the sum of the squares, we could have the third root of the sum of the cubes, or what have you. Yeah? And there are many others, right? So a surface embedded in R3, equipped with the geodesic distance, is itself a metric space. Notice that it isn't inheriting the metric structure of R2 in that case, right? These are different objects. It's not like one is a subset of the other, thanks to my choice of D here. Yeah? And in fact, they don't even have to be finite dimensional. So for instance, the set of smooth functions can be considered kind of like a metric space if I put this funny norm here where I subtract and square and integrate, kind of like that dot product that we talked about before. Yeah. So metric space is an incredibly generic object. Another good example in computer science is a graph, right? So a graph equipped with the shortest path distance is a discrete metric space. Right? Discrete metric spaces are kind of nice because they're just the list of numbers from 1 to n equipped with a matrix, an n by n matrix of distance values. Yeah, that's really what a discrete metric space is. Okay, so hopefully that definition makes some sense. And so when we talk about embedding, the question is, I take one metric space and I want to smash it into another, and see how much structure I can preserve when I do that. Yeah, so let's say that I can embed a one metric space into another and not distort the distances at all, right? So there's an exacted embedding, right? So for example, I have those 2 points equipped with distance 1. I can obviously embed those on the real line in a pretty easy fashion, like 0 and 1. What would that map be called? What property does that have? Anybody know? This is a term we're going to see a lot in the coming weeks. It's called an isometry. So an isometry is a map from one metric space into another that preserves pairwise distances, right? So in other words, d of x comma y equals d of phi of x comma phi of y. You need to write that down. I think that makes some sense. Okay, and there are many examples of isometries, and we've already seen some, right? So if I take a sheet of paper and I bend it, this is an isometry into its image because paper bends without stretching, roughly. So origami in some sense is the art of isometric deformations of a sheet of paper. But there are many others, and in some sense you could think of the problems we're considering today as the quest to find or approximate isometries from one space into another. And there's many reasons to do this, right? So for example, maybe I have some really crazy space where my data really lives, but I can roughly embed it into Rn, and there are plenty of really fast computational geometry algorithms that work in Euclidean space. And so maybe my first step in my algorithm is embed and then do some fast algorithm to approximate the calculation that really should happen in this crazy curve space. Right? That would be a good example. In fact, in computer science theory, that's a very common one. Yeah? Right. Does anybody know the famous lemma that justifies this trick in algorithms a lot? You've probably seen it. You might not have realized it's just an embedding theorem. It's called the Johnson-Lindenstrauss lemma, right? which justifies that you can often embed spaces into one another where, in that case, what they care about is the number of dimensions in the embedding space, right? You want it to be small because it has bearing on the amount of math you have to do in every step of your algorithm. And so that's a really critical one to get right. In fact, it's kind of a cool lemma. It kind of says you just project randomly and you can do pretty well. Okay, so for now, the first question we should ask is, can I always embed a metric space isometrically into Rn? So I give you some arbitrary metric space. So I give you, I don't know, some weird set plus a distance function. The question is, can I always find a way to jam that thing into Euclidean space, maybe equipped with the L2 metric? How many of us vote yes? How many of us are tired of voting? I don't care. How many of us vote no? Yeah, so you guys are absolutely right. So for an obvious example here is that space of infinitely differentiable functions we already talked about, right? This is an infinite dimensional space, yeah? But the set of functions is really big. There's a lot of functions out there. But Rn has n dimensions, so clearly something went wrong. Yeah. Okay, fine. So let's play a bit of a game here. So fine. So the space of functions is really big. Let's consider some smaller spaces. Yeah. So in fact, let's consider the smallest possible one. So let's say I have a finite metric space. So I literally have just an n by n matrix of pairwise distances between points. Yeah. What do I know about that matrix? Just that if I take any triplet, it satisfies the triangle inequality. So now I'll ask the same question. If I give you an n by n matrix of pairwise distances between points, can you give me back an embedding into Rn, or even R big N for like some large n? I always vote yes. Somehow it feels tractable, right? How many vote no? Yeah, so the no's actually have it. So the first group was wrong. And this is surprising. So let me give you a counterexample. In fact, here's a counterexample composed of 4 points. So my metric space here is the set A, B, C, D. And I've given you the distance metric. You guys can go home and check that this satisfies the triangle inequality. Take every triplet and just check the inequality. And let's logic our way through this. So first of all, let's see. So distance from A to B and A to D and B to D is equal to 1. Yeah? So let's say that I were able to embed into Euclidean space, right? So what do I know so far? Well, I know that these two things are equidistant to one another. Okay, and I have that from A to B, A to C, and B to C. So let's see. A to B, that distance is 2. That's clearly follows from the first guy. Yeah? At least bounded that way. And so let's look at these first 3 things together, right? A to B that distance is 2. These two distances are 1. So kind of you just added a rigid structure, right? You just showed that A, B, and D are collinear with D right in the midpoint. Okay, but now things are going to get funky because if A and C are distance 2 apart, B and C are distance 2 apart. So C is over here, and it's kind of an isosceles triangle so far. Or no, it's not. It's equilateral. I'm sorry. This is length 2, 2, 2. And then I'm just going to do one evil thing, which is add a struct of length 1.5, which is this distance here. Is this the height of an equilateral triangle? No. Yeah, so there's your counterexample. So you can just get it by computational, like not even computational geometry, just high school geometry. Right? So it turns out even a 4-point metric space you cannot embed into Rn. Yeah?
Can you also kind of look at that as like, if you had, say, like some sort of like hyperbolic space, which is like you took a triangle and then you took a geodesic between the 2 endpoints?
Oh boy. Yeah, I guess that's kind of right. I mean, this distance is smaller than what you would expect here. And I guess hyperbolic space kind of has that property, but right, like whenever people draw hyperbolic triangles, they always draw a triangle with like a little thing in it. I think formalizing that would be a little tricky. But here we're not a hyperbolic space, we're in flat space, which is Rn.
I'm just saying like this is just, you could just imagine this is just taking 4 points from hyperbolic space. And they're just pointing out that like, since they're 4 points, they're going to live in some three-dimensional hyperplane. Flat, and they can't be flat.
Sure, I'll have to think about that.
Well, yeah,
But there's a much simpler argument, which is just to draw a picture.
you're totally contradicting my intuition here, so this is really good.
Yeah, no, it's totally counterintuitive that if you have 4 points with a metric space, you cannot embed this into Rn for any n. Yeah, this is somehow surprising. By the way, for 3 points, what do you guys think? Yeah, it's called the triangle inequality for a reason. You can embed 3 like that. That's fine. Okay. Right. So already you can see that our task is a little bit opposed, right? In general, finding embeddings of data is quite tricky, and we're going to have to expect to be approximate, right? Because already we can see it's a very rigid problem, and it's not super intuitive what metric spaces are embeddable and which ones aren't. We'll come back to that a little bit. And by the way, this is connected to all kinds of scary theories of math, right? Things about rigidity and so on. As a contrasting example, so I gave you the negative result first. I thought I'd give you a positive one too, just for fun. So let's consider a different metric on Rn. Right? So our space is going to continue to be Rn, like tuples of n values. But now I'm going to put the norm of a vector in Rn isn't the square root of the sum of the squares. It's the largest absolute value of any element in a vector. This is the infinity norm. Agnes, you look very puzzled. How can I help you out?
I'm following. I'm just.
You just focused. That's great. Yeah. So this thing satisfies the conditions you need to be a norm, and you can check that if you do this thing of x minus y, you'll get a triangle inequality. That kind of follows from the triangle inequality that's hiding in the absolute value here. Okay. So this is a weird space. For one, by the way, what's the unit circle in the L infinity norm? Let's say that we're on the plane. Yeah, it's a square, right? Because these are all the points where one of the coordinates equals 1. Yeah? So it puts a weird geometry on the space. Okay, and what I claim is that every finite metric space embeds isometrically into L infinity. So notice that we were able to say something, right? Which is we can take finite metric spaces and embed them into some space that we know about, just not L2. Yeah? Anybody know what this construction looks like? It's pretty simple in retrospect, but it's one that I actually hadn't seen before. This is called the Frichet embedding. Okay, and the basic idea, I'm going to get my notes because this is sign mistake prone. Right, so what I'm going to do, let's say that I have a metric space, and I'm going to write my metric space. Here, M stands for metric and not manifold, I'm sorry. And I'm going to think of my metric space, I guess that should be a set, sorry, as A1, AN, where A is just a generic letter to stand for thing in a set. Okay, and I remember that I now have a distance function d, which takes in two numbers in M and outputs a positive number, which is the distance between them. Okay? So what do I need to show, to prove this kind of proposition? I'm going to do it in a constructive way. Well, I just need a map that takes every A to a vector in Rn equipped with this norm. Okay, so let's do that. Any guess what that map could be, by the way, before I...
Each dimension be a distance somehow?
Exactly, that's precisely the right idea. In fact, in some sense, that's the only information we have at our disposal, right? Which is we have this n by n matrix of distances. So in some sense, that gives you, an embedding by just like grabbing rows or columns of that matrix. And indeed, Fréchet had the brilliant idea of just kind of checking. In fact, I think the history of this fact was they kind of were using that as the embedding, went back and checked that, like, indeed, if, reverse engineered the right norm for which this is the embedding. But in any event, okay, so let's define the following, which is, right, remember, so phi is going to go from M into Rn equipped with this infinity norm, okay? And, right, and in particular, our map, phi of AK, right? So this is like the signature of this point in my metric space. It's just going to be a row out of my matrix. So in particular, I'm going to do the following. So this is dA1 AK, dA2, all the way to D. Yeah, so this is called the Fréchet embedding. You guys see that this is complicated notation for grab a row out of your distance matrix. Okay, fabulous. So what do we have to check? Well, we need to check that distances in this embedding are distances in our metric space, right? That's what checks if it's an isometry. Yeah. So in particular, the object that we need to check. Oh boy. All right. The object that we need to check is the following distance function. Conveniently, it has finitely many values, right? Because we're in a finite set. Minus phi. Right? So the thing that we're trying to check is whether this thing is equal to d. And notice that conveniently we've kind of defined phi in terms of d, so it's going to be not so hard to do that. By the way, let's give an explicit expression for what this thing is. This is the max over all k of the distance between what? Well, remember that this is really this value here, right? So this is kind of like the distance. I'm going to write it down and then explain it. Like that. So you see, because these are the individual elements of these vectors for element I and element J, right? So this is taking the max of the absolute value of all the differences. This is the L infinity norm. Everybody with me so far? This is the thing we got to check. Okay. So as usual, let's see here. One way to check if two things are equal is to check if one is bigger than the other and one is smaller than the other, right? I guess greater than or equal to and less than or equal to. So let's do that. So first, let's do the easy direction. So, right. So first, we want to check if this is greater than or equal to that. This is immediately true, right? Because this is defined to be the max over all k. Right, so the max is greater than or equal to choosing any particular k. Yeah, so let's choose k equals I. Right? Well, then what happens? So what is this expression? Well, when k equals I, this first value is what? 0. Second value is d of ai aj. Right? So what did we just show? We showed that this value is greater than or equal to d of ai aj. So we're good. Yeah? Hopefully it's okay. I'm not writing this down. It is in the course notes written out, but I think this is the easier direction. Okay, so now let's do the other one. Okay. So in some sense, we kind of know going into this proof, we're going to have to use all the properties we have of a metric space. Yeah? So we've already kind of used symmetry, we've already used positivity. What haven't we used yet? Triangle inequality, like the one thing that makes a metric space, keeps it up at night. Yeah? So let's apply the triangle inequality twice to derive a small corollary of the triangle inequality, and then we're going to plug that back in. Yeah? So in particular, what do we know? Well, we know that the distance from AI to AK is upper bounded by the distance where I go through J, right? So distance AI, AJ, plus the distance from AJ to AK, right? This is just triangle inequality. And similarly, we know that the distance from AJ to AK, well, I can go through AI this time, yeah? That this is less than or equal to the distance from AI to AJ plus the distance AI to AK. I keep looking back in my notes because I'm trying to choose the ordering to make it easier to read in a second, okay? But these are just, these are both the triangle inequality. Okay, so what can I do? Well, one thing I can do is say, okay, so let's look at the following value, which is the absolute value of the distance from AK to AI. I always get the reverse triangle inequality backward. Minus the distance AK to AJ. Yeah? Well, let's see if I can get something that looks like this in this expression. So we have AKAI, which is here, yeah, minus AKAJ, if I move that to the left-hand side. So it's upper bounded by the distance from AI to AJ. And similarly, if I look at the second expression, AKAI, now it's on the right-hand side, minus this thing, right? So minus this expression is also upper bounded. So when I put these two guys together, what I show is that this absolute value is upper bounded by the d of AI AJ. It's called the reverse triangle inequality. Are you with me so far? These are just boring calculations. Okay. So in particular, one thing I can do, so this is a value that's true for all k. Yeah? So in particular, I can say that the max over all possible k of this expression is still upper bounded. Notice the right-hand side has no dependence on k. Yeah? Well, what is this value? This is exactly the norm that we wrote down. And so we just proved the inequality in the other direction. Cool? All right, so what did we just show? We just showed that if we have a finite metric space, we can embed it into L infinity. That's kind of like a fun fact. You can take that to bar trivia tonight. Incidentally, this proof extends pretty easily to infinite dimensional spaces, right? You just kind of think of these as sequences instead of finite values. So there's a very weak version of this theorem, which is still true. Is it particularly useful? No, it's not clear why you would want an embedding into L infinity. I think there are very few applications that would call for that, right? I mean, these squares doesn't really make sense. You can't even do vector arithmetic in this space. It's a weird space. But at least it's nice to know that we can embed somewhere. I think it's kind of where we're at, right? And in some sense, you know, it tells you more about L infinity than it tells you about the space you're embedding, right? What it says is that L infinity is somehow an extremely generic thing as a metric space object. Yeah. Yeah. So anyway, that's our argument so far. And really, this depends on a nice construction. So I'd say the proof here isn't terribly useful, but there's a construction hiding in here, which is that this is a constructive proof, right? Which is just to use the distance to a bunch of points as you're embedding. And this is actually a hack that you see in a lot of computational application, which is, well, in the absence of any other information, I might as well use my distances as an embedding. And the intuition here makes a lot of sense, right? It's saying that 2 points that are close in my embedding, well, somehow spiritually, why are they close? Well, one reason to understand that is they're close because their distance to everything else is close. right? And that's really the trick that's being applied here. So the definition of Frechet embedding is actually slightly more general than what I gave you there. So the Frechet embedding in our construction here is just the distance to a single point, right? So we use the vector of distances to all the points in my set as my embedding into Rn. The actual Frechet embedding does kind of something sneaky, which is I take a bunch of subsets of my metric space, S1 to SR. So these don't have to be composed of one point. They could be, like if I'm on a surface, they could be like little patches or something. Does that make sense? And I'll define this distance from a point to a set to be the min over all points in the set of the distance. Right? So like if I have, a set on the board, and I have a point, then it's sort of the length of the closest projection. Yep. Then essentially the Frechet embedding with respect to this set of sets, I know that's hard to parse, is the vector of distance values to each of those sets, right? So in our previous construction, what would be like S sub I? Just as a sanity check. Exactly. So in this construction, if I wanted to call this a Frechet embedding, I would write that, right? Because that's the distance to one point. That makes sense to everybody? Cool. And so this is just like a very generic trick for kind of cooking up embeddings out of distance functions. And it's a useful one, both mathematically and practically, really. This is one of the standard ways to get an embedding out of metric space data. Okay? So anyway, now we have one positive story and one negative story, and they're somehow on very opposite extremes, right? I can embed nothing exactly into Rn, no matter what n is, if I equivalent with the L2 distance. On the other hand, I can embed just about everything into L infinity, but it's not clear what that buys me other than just like a fun fact. Yeah? So the reality is what we probably care about more is approximate embedding. Like we allow a little bit of wiggle room in modifying the distance function while we do solve that embedding problem, rather than this thing, which is kind of like setting a bunch of toothpicks with particular lengths and seeing if we can glue them together in a way that fits into the space we care about. Yeah? And so in particular, there are a lot of different ways to measure the quality of an embedding. Here are sort of three common measures that people use actually in computer science theory. By the way, everything we're doing so far is largely lifted from algorithms world, where they want to kind of project into a lower dimension and then do computation there to slice out a few multiplies worth of work, or sometimes asymptotically many. But in any event, let's take a look here. So our embedding here is a function f, and we have two different distance metrics on our spaces, mu and rho. I guess D1 and D2 probably would have been more reasonable choices of notation, but your instructor forgot to fix his slides until this morning. So in any event, if we think of expansion, take a look at what it's doing. It's like the ratio of the, this is the distance in the embedding versus the distance where you started, and you're taking the max. Right? So this is kind of like the biggest distortion of any distance in my original space. Right? The contraction is the opposite of that. And then the distortion, and this really is a measure that appears in computer science theory. I've referenced some notes. Essentially just the product of these two things. Notice I was sneaky and I chose both of them to be big when you have something that's not isometric. That's what makes sense to multiply. Now, so this is a pretty reasonable notion of distortion. Essentially what it's trying to measure is to make sure that no pair of points gets kind of too far away from each other or squashed together too much. That makes sense? Okay. So, great, so we know that we can't embed spaces into our Rn equivalent with the L2 norm exactly, but now we've just given us some wiggle room, right? We might ask a question like, if I give myself a distortion budget of 3, can I embed my my data into this space with that distortion? Okay, now what do we vote? Can we embed into L2? Do we think so? Yeah, we do. At least Monday does. All right, so fine. So what's our algorithm? How are we going to do that? No idea. Yeah, in fact, that's totally reasonable because this is a really subtle fact from metric space theory. It's actually named after Bourgain. Does anybody know who this person is? He recently passed away. Yeah. So this is, I believe he has a Fields Medal. He's a very famous mathematician. No? I think he does. No? He might not have a Fields Medal, but he's kind of a big deal. And yeah. But in any event, just recently passed away, so there's some history hiding there. Yeah, I know, right? But in any event, one of many interesting theories that this gentleman derived involves embedding. And it's kind of a surprising fact, which in this version of his theorem relies on a coin flip. I think there's some deterministic version as well. And basically the idea here is I still have a finite metric space, so it's comprised of endpoints here. Bourgain, I think, is sort of closer to the computer science theory world, and they're mostly interested in finite data. And actually, for any p greater than or equal to 1, so this includes not just the norm, which is the square root of the sum of the squares, but also all the other ones, including the infinity norm, but we already kind of knew that. Essentially, what he shows is that I can embed with distortion, which is proportional to the logarithm of the number of points. So it grows very slowly in the size of your data point into Rm, where m here it also kind of looks like the log of n, the log squared. So m grows a little faster. So you should take a minute to parse this because it's kind of hard to read, right? So what is the basic point here is that roughly logarithmically in the size of your data, you can find an embedding that has pretty low distortion. That's the takeaway of Bourgain's theorem here. And this is not a theorem that we're going to prove in this class, but you guys should go home and take a look. If I remember, it's actually not terribly complicated. It just depends on some kind of concentration style inequality from probability theory. Okay, so right, and this distortion bound actually was improved. So you can get rid of the square if you're willing to divide by p here. This is, I believe, a different Matusik from the one in the ECS department here, but I could be wrong. Okay, so Bourgain's theorem is a little complicated, but the construction is actually extremely simple, which is pretty cool. And this is something you can code up at home. You can actually kind of play with it in MATLAB, and this is a thing that works in a regime which is not like super tiny, which caught me by surprise. Actually, my old slides for this course used to say, this is mostly of theoretical interest. But it's actually, I don't know if that's true. This is a construction which is easy to code, and actually the asymptotics don't require you to take n to be some ridiculously huge number that's bigger than the size of the universe. So the basic trick of Bourgain's construction actually also leverages the same embedding we already talked about, which is the Fréchet embedding. But rather than having all of those S be singleton points, he gives you a random process for constructing each set S sub I, and which is kind of sneaky. So the trick is you construct a logarithmic number of these sets. So your Fréchet embedding has a logarithmic number of dimensions to it. And for each one of these, you flip a coin, and with probability 2 to the minus j, so that just depends on what set you're in. So different sets have sort of different numbers of elements on average. You flip a coin and just throw that element into that set with that probability. So in other words, like if you think about what his algorithm or his construction is doing, right? So the first time you make a set, let's see. I guess actually the first distance function is really boring. It's just distance to, I guess just all zeros the way this is notated here. The second one, right, with probability 1/2, I add each element in my set to the thing to whom I'm computing the distance in my Fréchet embedding. The third one with probability 1/4 and so on. Yeah? And so in other words, kind of a picture you have in mind, here's my metric space I'm trying to embed. The first thing he does is kind of densely sample a bunch of points inside of the metric space. And the embedding is like just these small values of distances to the closest point in this kind of dense sample. And then he sparsifies and sparsifies and sparsifies. So there's some kind of multi-scale thing happening here. This is obviously a very careful construction. You can see there's some magic numbers here, like 576, which make this thing work. I think that's pretty common in theory, and then we hide that with the big O. Yeah. But in any event, the actual embedding is quite simple, right? You just do a bunch of coin flips, you keep track of the set S, and then your embedding you just read off of a formula. It's really not so bad. Yeah. This is a nice construction, and this works. One of the kind of funny things you might notice about this algorithm, do you see the number p anywhere? No. Yeah? This is a little bit bizarre. It turns out that this value of p, like exactly what metric you put on our end, doesn't really matter for this theoretical fact. This might also tell you this is extremely coarse, right? Like I wouldn't use this as like a perfect approximation of a distance function, right? So anyway, Yeah, so this is a pretty central result in computer science theory, right? Because think about what it's saying, right? Like, so if I do computation on a metric space, every time I want to touch all my points, I've kind of incurred a factor of n, right? What this is saying is if my algorithm really only depends on distances, if I first compute this embedding, I can do a pretty good job, but in log n time instead of n time. And so this has some nice consequences for making algorithms faster if you're willing to be approximate. Yeah? And this is pretty different from our discussion of like computer graphics the last couple days, yeah? Which is fun. Okay, so that's sort of the very extremely broad strokes theory of embedding, right? So now we have two extremes, right? We can embed everything into L infinity exactly. We can embed almost nothing into L2 exactly. We can embed almost everything into LP nearly exactly. But all of these things are extremely rough estimates and not terribly practical, right? A lot of these are sort of more in the theoretical realm. So now let's change our focus a bit and talk about some algorithms that people use in practice. So the simplest algorithm for embedding is something called multidimensional scaling. Most have used this. If you're in data science, you may have seen it. So MDS is a fancy phrase with many syllables, which secretly means eigenvalues. And let's see why. So MDS specifically is for the Euclidean embedding. And initially, the way we're going to motivate it is we're going to say, let's say I have a bunch of points in Rn, and by accident, I lost my points. And instead, you gave me this function here, right? So Fernando was writing some code. He computed pairwise distances between a bunch of points, just equipped with the L2 norm. But by accident, he lost the x's, and he just has the p. So the first question is, if we knew that P came from a pairwise distance matrix, could we recover the point locations, specifically in this case, right? So this is how we're avoiding that embedding question of like, but should we? Right? The answer here is yes, like we know it came from something. And then we'll see that it still gives you a reasonable approximation, even if you don't. Yeah? So first of all, what do you guys think? If I'm given P, can I reconstruct the x's? Yeah? We see some nods? Yeah, more nods? Well, you shouldn't, because that's completely wrong. Yeah, because like think about like if I take all the x's and I just shift by a constant, right? The distances didn't change. Yeah, so I did lose some information when I embedded. Yeah, but I can recover n embedding with the same distances. That we can do. It just might not be the same one. Yeah? In fact, it's sort of the same one up to rigid motion, like rotation, translation, and reflection. Okay. So now, some more calculations. Cool. So let's see here. So let's think about this matrix P and do basically the only thing we know how to do to that matrix, which is expand the square. And in doing that, we're going to reveal a slightly different matrix, which is easier to work with, which is basically the matrix of dot products. Yep. So in particular, okay, so what is Pij? It's just xi minus xj, 2 norms squared. Of course, this is the same as xi minus xj dot product with itself. Your instructor was up very late last night writing a document he didn't know he had to write, so if I make a stupid mistake, I apologize. Okay, and of course we can expand this thing, and this is really the norm of xi plus the norm of xj squared minus 2, the xi dot xj. Hopefully this isn't terribly surprising. Okay, so let's define a new matrix, and we're going to define Gij to be equal to xi dot product with xj. Okay, so this is the matrix of dot products. This is the matrix of distances, and these things are closely related to one another, unsurprisingly. Yeah. By the way, let's all be grown up. So we have a matrix X, which you can think of like x1 as the first column, x2 as the second column, and so on. Right? Then can anybody give me an expression for G? I know many of you can. When I say can anybody, the answer should be yes, I can, and you give me the expression. So let's see a show of hands. Can somebody help me out here? Yeah, x transpose times x. Right? Because we take all the vectors, we flip them on their side, multiply, gives you dot products. Yeah? Okay. That's an x. All right. So question is, what is the relationship between G, X, and P, because those are the things we're going to be pushing around for quite a while today. Okay. Well, in particular, take a look at this expression here. Right? I've done a sloppy job of my board writing here. So I'm going to erase this thing. But notice that I can read all three of these numbers off from G. Right? So for instance, this is x, the norm of xi squared. Right? So this is xi dot product with itself. So this is secretly GII. Right? This is xj dot product with itself. So it's GJJ. And this is xi dot product xj. Cool. So there's a nice relationship between the squared distance matrix and the dot product matrix G. So does anybody know what G stands for? It stands for gram. This is the gram matrix. Yep. There's a really big version of it on a slide. Okay. By the way, this is the beginning of a lot of techniques in sort of the optimization-oriented machine learning, right? Because notice that this relationship is linear. Yeah, and so if I want to optimize for one or the other of these two objects, I can do that, and they're both kind of equally easy to access. There's nothing crazy that happens in between. And furthermore, G is a semi-definite matrix, right? So if you're into semi-definite programming, this is the kind of the beginning of that story. Okay, so right, so we can write based on this expression here. If I want to vectorize it, like I don't want to write it in terms of indices. I can do that. And what I get is that P is equal to minus 2 times the gram matrix, right? That's this term, plus the diagonal elements of G, right? That's like the vector of the GIIs, times the vector of all ones transpose, plus times the diagonal. By the way, whenever you guys see expressions like this is really not terribly complicated. So this is a column vector, and this is the vector of all ones. And so secretly what this is doing is it's just taking this vector and copying it a bunch of times into all the columns of a matrix, and vice versa. This is doing that to all the rows. Right? And that kind of makes sense because you have an II, which is like, row, JJ, which is like column. Cool. Everybody with me so far? Fabulous. Okay, so what have I done so far? I've told you if I know P, I know G, right? We know that knowing P or G is not sufficient to reconstruct, but we think we can get it up to rigid motion. The next question is, let's say that I knew G. How could I get an embedding of my data that satisfies the dot products that are encoded in G? So what are positive definite matrices, like symmetric positive definite matrices, screaming out to do? Have eigen stuff done to them. Yeah? So let's do that. So let's say that I write G. I take its eigen decomposition, right? So I can write it as Q, lambda, Q transpose. Furthermore, well, in general, maybe I think of Q as an n by R matrix where R is the rank, right? So the columns of Q are orthogonal. And I make the following definition, and this is where the notation gets a little bit sneaky. I'm going to define x bar to be equal to the square root of the eigenvalues multiplied by Q transpose. Why did I do that? Well, take a look. So if I construct the gram matrix of these things, what is that? Well, that's Q lambda, right? Because you get two of these when you multiply. Q transpose. Yeah? Well, that's exactly what we want, right? That's G. Yep. So what do we know so far? We know we have to be a little bit careful how we phrase it. We have to be a little democratic, right? We know that if G came from dot products, then we could recover another embedding, which may not be the one that we started with, but has the same dot products. Okay? And everything here is an equality sign. There's no approximation that's happened yet. So what do you think we're going to do to embed a pairwise distance matrix? Well, first thing we'll do is square it. And then we'll go from that thing to an approximation to the gram matrix, and then use its eigenvectors as sort of an approximate embedding, even if it turns out our distance matrix didn't come from points in Rn to begin with. Okay? So that's going to be the kind of sleight of hand that happens. So let's see what that looks like. So in particular, the one thing that we're missing is that the input data to our problem is not g, it's p, right? It's the pairwise distances between points, squared. By the way, if you guys have looked at old versions of the course notes or slides, I used d instead of p, and that was really not a good idea, because p is the squared distance matrix. So I've tried to relabel it here. If you guys catch one that's missing, let me know. OK. So far, I've told you how to go from G to P, but we really want to go the other way if we want to apply this eigen thing to our reconstruction problem. Does that make sense? Cool. So let's do that. Yep. So let's solve this expression for G. Can we do that? Well, not totally easily, because G appears 3 times. But let's pretend like that weren't the case. Yeah. So in particular, let's isolate this appearance of G here, because somehow that's the most accessible looking one. Yeah. And now I switch to my other notes, because I panicked before class. I thought I couldn't get it to work, but I can. Yes, we can. OK, so let's say, so in particular, we have that G is equal to 1/2. And now we're just going to read off all this stuff, right? So this is diagonal of G times the vector of all ones. Plus the vector of all ones times the diagonal minus p. OK. So we're almost there. Right. So now I'm going to do something really sneaky. I'm going to say, remember, I can translate my embedding around any way that I want. And if I translate points, the pairwise distances don't change, as long as I translate them all by the same thing. So in particular, I can always translate any set of points so that they average to 0. Right? This is going to be just something that makes my life easier. So I'm going to assume that in the output that I want to compute, the sum of xi is equal to 0. And I always know that a solution to my problem exists with this property, because I could have translated to that. OK? So now we're going to define a handy matrix here, which is J. And is equal to the identity minus 1/n times the vector of all ones times this transpose. Anybody know what this matrix is? We're going to continue dredging up all the linear algebra that you haven't thought about in a long time. That was like a really strange noise that just came from the whole classroom. OK, let's see. So it's the identity minus some multiple of the matrix of all ones. That's actually the wrong way to think about this thing. So in particular, what is the rank of the second term here? Just rank 1, right? I mean, it's just the outer product of 2 vectors. Yeah? So what is this second piece? This is the projection onto the vector of all ones. Do you see that? It takes the dot product with this thing and then it scales. So what's the identity minus the projection? It's the projection onto the space orthogonal to the vector of all ones. Cool. So that's the way to think about J. OK? So what is the corollary of this fact? So the sum of all of our xi's is equal to 0. Yeah. So in particular, what do we know? Yeah, we know that if we sum up all the xi's, what happens? Yeah, I get 0. Right? So in other words, so if I sum up all the xi's, I get 0. A different way of saying that is that if I project out the thing that wants the sum to be 0, nothing happens. Yeah? So a fancy way of writing that, hopefully, which is here, is that if I've centered my data, x is equal to x times j. Do you see that? Notice I put it on the right-hand side because it's acting on the columns. It's combining the different x's. OK. Cool. So now I'm going to plug that thing into here, and we're going to see that a magic trick happens. OK? Right. So let's do that real fast. Ouch. Right. Okay, right. So in particular, what do I know? I know that the Gram matrix, well, is equal to X transpose times X, but X is equal to X times J. So this thing is really equal to J transpose X, J, right? By that relationship here. But then this thing is also the Gram matrix. Yeah? So this is J transpose times the Gram matrix times J. I made up this argument in my office this morning, so if there's something wrong, you should tell me. But I think this is okay. Okay? So this is a little bit of a sneaky trick, right? In other words, it's saying that if I conjugate Gram matrix with J, nothing happens, which we kind of knew. Okay, fabulous. So now, what does that mean? So let's plug that relationship into our expression for G, right? So in particular, I get that G is equal to 1/2 J transpose times, diagonal of G times 1 transpose plus 1 transpose diagonal of G minus P. Okay, times J. So what do you think these two terms are going to equal? Just have to guess. Like where I'm headed with this. Well, it turns out when I conjugate them with J, I'm going to get 0. Okay, so let's see why that is. So maybe let's look at this one so I don't have to deal with J transpose. Yeah. Oh, I'm sorry. Thank you. Okay, great. So let's take a look at that second guy. So this is 1 times the diagonal of G times J, right? So what is this object? Well, this guy is summing all of the rows, right? That's his job in life, right? Or all the columns, rather. Is that right? Wait, what did I do wrong? Oh, I forgot. There's a J transpose thing on the left. Okay. Sorry. J transpose diag G. All right. Just for my own sanity, we're going to swap to the first term so that it agrees with my notes, because your instructor's an idiot and can't do live math. Okay. Right. I'm bad at transposes. I'm sorry. Okay, so this is, obviously if this is 0, this is 0, right? They're just transposed with each other. Okay, so we're just going to look at this expression. We're going to ignore that last J. Whew. Okay, so what's going on here? Let's see here. So what I'm doing, so let's look at this expression first. This is taking the diagonal of G, and it's just repeating it a bunch of times. Yeah? Or if we look at this expression, oh boy, why am I getting myself confused? You know, let's just write out the expression instead of trying to make a high-level argument. Okay, so what is J here? So J is the identity minus n times. It's been all morning staring at this. It's embarrassing. Times di. Okay, yeah, that'll work. Okay, right. So let's expand this this product here. So what do we get? We get, that's the first term, right? Because it's the identity. And what is this thing? Well, think about what it's doing. So this is 1 transpose. Okay, this is gonna work out. So 1 transpose times diagonal G. This is the sum of all the elements along the diagonal. I'm dividing by n. So this is the average diagonal value in G. So let's notate that as, okay? And then it's just multiplied by all ones, right? So what is this? It's taking a vector and then subtracting off of its average. Do you see that? Ah, okay. Oh man, did I still manage to get the transposing correct here? What was that?
The one, the last one. I mean, the one on the right side of the mean.
Oh. Oh, that's fine. This is just a scalar. Right. So what am I missing? Well, I guess there's a j on the right-hand side of this thing here, too. Okay, rather than wasting a bunch of people's time, I can tell you the high-level argument, and then you guys can fill in the calculation. I'll put it on Piazza. What's missing here, what is the sum of this vector? 0, right? Because the sum, I mean, what did I do? I just subtracted off the average, right? And so in effect, this thing is going to sum this stuff up, but I'm going to make it 0. Okay, so my apologies for getting indices wrong, but I'll make that true on Piazza, okay? My apologies. Whew. Ah, it's embarrassing. That's okay. At least once every other lecture, I have to get myself totally confused. Okay, so assuming that that is true, what can I say? Well, in this case, what I get is that G is equal to, well, minus 1/2 J transpose P J, because the other terms do indeed vanish, despite your instructor's poor math skills. Okay? So what does that mean? If I want to derive the multidimensional scaling algorithm, is quite straightforward. Right? So remember, as input, I'm given pairwise distances. I take that whole matrix and I just square it element-wise, and I have pairwise squared distances. Yeah? I can go from that to the Gram matrix under the assumption that my points sum to 0, which is an okay assumption to make, by just conjugating with J, multiplying by minus 1/2. And then to get my embedding, I take the eigenvectors, and I'm done. Yeah? So at the end of the day, here's the algorithm. So it takes place in a few steps. The first thing is something called double centering, where essentially I'm just subtracting off the mean of the rows and columns. Yeah, I'm still trying to convince myself that thing's true, but that's not a good use of everybody's time. Right. Then I just use the MDS embedding. And essentially, what did we prove if you kind of turn our argument backward? We showed that if my data came from pairwise distances between points in Rn, then this thing will recover an embedding with the same distances. It won't give you the same embedding, but it'll give you something similar up to rotation and translation. Okay? Yeah?
If our data come from R3 and we prescribe the 4-point that is not collinear,
Ah.
we recover the exact embedding?
No. Yeah, so the question was, if our data was in R3, can we, but somehow n was bigger than 3. Is that? Yeah, I guess that's right. So I have more than 3 points, but they're in R3. Can I get the right embedding? And just I can get the right dimensionality, right? Because what are the eigenvalues going to be beyond the third one? 0. Right, so I can slice those dimensions out, but what I can't do is I still only know my points up to rigid motion in R3.
Yeah, but if we prescribe like 4 points.
Oh, sure, yeah. If I know my points up to rigid motion, I give 4 points, then I guess you're right. That fixes that problem. Yeah. Okay, so my apologies for a small arithmetic mistake, but that aside, the actual algorithm is quite simple, right? So I compute pairwise squared distances, I center it, and that basically converts from distances to dot products. And then once I have those, the eigenvectors, the dot product matrix, are exactly what I need for my embedding. And this really is the standard technique for embedding. It's totally boring. Yeah? And people use even when their data is not Euclidean. What do you think happens to the eigenvalues in that case? Well, they decay, but they don't necessarily go to 0. And so a pretty common practice is to just kind of truncate. It's very hard to prove much about that, but it seems to work for a lot of data that's out there. Right? So as one small example, these people managed to embed a nanotube given distances. I was looking at this experiment. This is a kind of one that appears in a famous treatment of this kind of material. And I think this is a completely made up experiment. I think what happened is they knew the 3D constructor, they computed exactly the distances they wanted, they threw away, and then they computed the eigenvalue, and like voila, the embedding came back. My bet is if you perturbed that distance matrix a little bit, you wouldn't get nearly this nice result. But in any event, it's kind of nice to see. Okay, so in our last few minutes, we'll start motivating a second algorithm. So notice this technique was a little heuristic, like it works perfectly for Euclidean data, but I haven't told you anything about when my data is in a space that's not Euclidean. There are two ways you could go with that, right? You could either go to like Bourgain's theorem and try to do something with non-Euclidean data, or you could say, great, well, if I have heuristic methods, I might as well cook up heuristic methods that make a little more sense, right? In particular, I mean, what was the goal that we set out with at the beginning of class? It was to conserve metric space structure, and then what we ended up doing was conserving dot products. That wasn't quite the same. They're close, but they're not quite the same. So the more obvious thing to do, that probably if I sent all of you guys home and asked for a reasonable way to embed your data, would be to set up some kind of nonlinear problem that looks something like this. So here, the xi's are my embedding, right? I'm given a matrix D naught. So if I want to cook up an objective function that measures how good my embedding is, the easiest thing to do is measure how good your embedding is, right? Not do all this centering and all this crazy stuff, right? And so here, notice that I've computed pairwise distance between every xi and xj. I've subtracted out the D naught, and then just squared and sum. So this is some kind of least squares problem. Is this a nice problem? No, right? I mean, so this expression contains like a square root, yeah? And then it's high, and then there's some, you know, unfortunately the square, like something happens to that square root before there's a square, yeah? So this is a pretty nasty expression to optimize. It's not convex. There's very little you can say about it. In fact, so this was proposed in a paper in the 1970s. I'm kind of amused. They called it scaling by majorizing a complicated function. So apparently they realized it was a difficult problem as well, or smack off for short, which is a terminology which we are now stuck with for the rest of forever. The more elegant terminology for this is called stress majorization, and we'll see why in a moment. Yes?
Is there any reason that you don't get rid of the square root by just squaring the d and squaring the distance?
Sure, you could, but then your objective would be quartic. It's still not particularly easy to optimize. Okay. Yeah. Yeah, so I mean, there are a lot of variations on this, and I'll call out a few after we talk about this one. One reason to do this is that we'll see there's a very elegant optimization algorithm for this particular objective. But it's non-convex. All we can say is it reaches a local optimum. Okay? So to do that, well, we only have one hammer. We might as well hit a bunch of nails. Essentially, all we're going to do is expand the square, right? But in this case, the thing that's going to be inside of the square is not linear. Yeah? So let's say that I took my potential function here, and I just took that square and I expanded it. Right? So the first term, well, for the purpose of our optimization problem, is a constant, right? There's no x's in there. The second term, well, let's defer that for a second. The third term is well, you know, the distance from xi to xj squared, right? A fancy way to put it actually is in terms of this J matrix. Yeah. So one thing you can check is that this is just a nice encoding of this expression right here. The same thing. And then finally, we're left over with this cross term, right? This is the sum, -2 times the sum of distances multiplied by distances in the two spaces. Yeah? So in this Smakov algorithm, they do a really sneaky trick here. This is kind of the theme in a lot of the multidimensional scaling literature, which is to say, our life would be a lot easier if we had a least squares problem. You know, that's just, we know how to do least squares. And the sad fact of life is that this is not one. So what they do is they say, okay, one thing I can do is just like squint a little bit and put a 2 here. And then what am I going to have to do? Well, I'm going to have to divide by that same number. Yeah? And that's the sneaky trick in this construction, is to say, okay, well, right, so what do we have? We have -2 times the sum over ij of the distance d naught ij times xi minus xj, 2, like that, right? That's our expression. Oh, oops, not squared. But let's say I wanted it squared. What would I have to do? Well, one way to get that square is to divide by the same value. Yeah? I haven't done anything. But what I'm going to do, which is a little tricky, is pretend like this is a constant, solve this problem, update the constant, and iterate. So in other words, I'm going to kind of absorb that into the d value, and then it looks like least squares. Yeah? So I'm going to construct a particular matrix. So this is actually an equality. I'm going to define a matrix B of x, right, where B of x has elements which are d divided by this value. Notice that there's like a little bit of circular reasoning so far. Like I have to know x to be able to use this expression. Yeah? But if I make this matrix, right, then just by exactly the same argument as over here, I get this fancy expression for our cross term. This thing is not quadratic Do you see that? Because b has division in it. Yeah, it looks quadratic because there are two things multiplied. There's an x there. Everyone with me so far? So all I did was divide and multiply by the same value. Okay, so why would I do that? So we're going to prove a quick lemma here, and then I guess we'll call it for the day, and next time we'll derive the algorithm. So let's define a particular function, tau, of x comma z. So this is a function that takes in two matrices and outputs a scalar. Okay, and tau is going to be exactly our expression above, but all I'm going to do is take two of the occurrences of x that I had before and call them z. Right, so what is tau of x comma x? It's our objective function, right? So this is just some kind of broadening of our objective function. Anybody know what this trick is called, by the way? This is a representative of a larger trick in optimization, which is one I never have any intuition for. This is called majorization. Okay, so right. And what we're going to prove about tau is it has this interesting property, which is that it is upper bounded, or it is lower bounded when I put x in twice. This is going to be the property that we need. Because essentially what this is saying is that, like, I'm going to write an optimization algorithm where my objective looks something like this. I have some function here, and somehow I have like a proxy like that I'm going to minimize. And because of the upper bound, I know that my objective decreases when I put in an x again. Right? That's the sort of picture to have in mind. Okay, so yeah, so let's prove this really quick. And this is actually just a side effect of the Cauchy-Schwarz inequality. Okay, so in particular, by Cauchy-Schwarz, our favorite, we know that for any I and j, xi minus xj, dot product with, and now we're just going to come up with two new vectors called zi and zj. The Cauchy-Schwarz inequality tells us that this is upper bounded by the product of the norms of these two guys. Like that. Okay, and now the trick to proving this lemma is to do kind of a funny rearrangement of this expression. So we're going to assume that all of these terms are non-zero, so we never use the same vector twice. And if that's true, then a different way of writing this is that this value, the distance from xi to xj, is upper bounded by xi, xj. Dot product with zi minus zj divided by the norm of zi. So this is just a rearrangement of this expression here. Okay, it's kind of a funny way to write Cauchy-Schwarz. Okay, so in that case, well, really the only term in our definition of tau that we have to worry about is the third guy, right? Everything else is the same in the two sides of our inequality. Yeah. So let's just look at him. So in particular, we have minus 2 times the trace of x b x transpose. Right. So this is starting from the left-hand side. Okay. We can just ignore the rest of the terms for now. Well, by definition, right, this is equal to minus 2 times the sum over ij of d naught ij xi minus x. Right? That's like the way that we define that matrix B. Okay. Well, now take a look. We have this funny expression here. Right? There's a minus here, so the inequality flips. So what do we get? We get that this is less than or equal to minus 2 times the sum over ij of d naught ij times xi minus xj dot product with, and now we're just going to have some generic z's. We don't know anything about the z's, but for any choice of them, zi minus zj divided by the norm of that thing. And that's just by plugging in this inequality. Cool? Well, we can kind of rearrange this expression a little bit. So this is minus 2 sum over ij of what? Well, d naught ij divided by the norm. Right, so all I'm going to do is move this norm to that term times the dot product like that. So like literally, this is just a visual rearrangement in some sense, yeah? But what is this thing? Well, this is exactly minus 2 times the trace of x, b, just by definition, right? That's how we chose this matrix B, right? Because remember, the B is the thing that's containing the 1 over distance term, right? And then these guys are the things that are giving dot products. Okay, so in effect, so that bounds just this term that involves x and z. Notice the other two terms only involve x anyway, and so that proves our lemma. And something that you can double check is equality exactly when x and z are proportional to one another, and this is just the equality case for the Cauchy-Schwarz inequality. Okay? Right, so I guess we're out of time. Our algorithm, which we'll derive next time, is extremely simple given this fact. So all we're going to do is in every step, we're going to choose x to minimize tau where I fix one of the two arguments to be the x from last time. And what we'll double check is that in every step of this algorithm, this Smakoff value has to decrease. This is like a two-liner following from this inequality here. And furthermore, we'll see that the expression for this minimizer is just, you can write it in closed form. Right? So it's just a formula you type in your computer, you iterate, and it converges. Yep. And what you get is a nice embedding. So here's a picture that compares a little bit. So here's a telephone call graph. So I guess these are all the different people that talk to each other back when we made phone calls. One of the issues with the MDS embedding is that oftentimes you get these kind of messy things. It doesn't really do, the approximation properties for MDS aren't great, and we haven't really even derived any, right? But here it really wants the edges to be length 1, and you can see that on the embedding. So something nice kind of happened here. Yep. So in any event, we're already over time, so we'll call it for the day, and next time we'll derive the iterations of Smakoff. My apologies for a small mathematical piece of confusion, but at this point you're used to it. So I'll see you guys next time.